Hello everyone. We are team number 51 and I am Marjani with my teammates Ashka and Neil present to you our project Skin Cancer Classification for the course of Neural Networks. Nowadays, machine learning has been greatly integrated in the healthcare systems. The techniques are being widely used for several problems in the healthcare industry. Skin cancer is one of the most common types of cancers globally, and to detect it correctly is one of the crucial tasks for the healthcare providers. And we want to leverage deep learning techniques to provide a solution for the same. Our task here is to classify the skin images as either malignant or benign, and we will consider this as a binary classification problem. Our dataset here is from Kaggle and consists of microscopic skin cell images which are either malignant or benign. And here is an example of how these skin cells look in our dataset. We have approximately 3,000 images from training and testing, and those have been divided into subfolders of benign and malignant. The image here do not have explicit labels and are in the form of subfolder names. So here we are performing label encoding. Here are the graphs of train label distribution and test label distribution, and as you can see, they are quite balanced. For pre-processing, we didn't have much to do as the color scheme is almost on the cream color, but we do various pre-processing techniques such as random flip, random zoom, resize, and then we normalize the image well. But we do data pipelining, which optimizes the overall speed of the code. The pipeline function augments, pre-processes, shuffles, and prefetches the images according to the buffer size, and thus increases the overall efficiency of our baseline model. For the baseline, we have used CNN. As you know, CNN is one of the most common neural networks in deep learning tasks as it is very proficient for image datasets. This is the generalized architecture of CNN. We have convolutional layer, max pooling layer, dense layer, and then we output the image. And from this, we have updated our CNN architecture. This is our baseline model, and we have 4 convolution layers. And after every 2 convolution layers, we have a max pooling layer, after which we flatten and have a dropout of 0.2. Our baseline CNN has Adam optimizer and binary cross entropy loss function as it is a binary classification problem, and the number of epochs are 10. The performance of our baseline is as follows. We have training, validation, and test accuracy of approximately 80%, which shows that how the model has converged correctly. The loss is also around 38%, which is a good measure. The main thing here is that we have a precision of 97%, which means that the model is very good at avoiding false positives. We have also attached our confusion matrix for further evaluation. This is the output of our baseline, and as you can see, we have the true and the predicted labels listed. These are very randomly picked samples from the dataset. To enhance our classification further, we have used transfer learning technique of vision transformers for object detection and image segmentation, as they are great at extracting high-level features from the skin lesion images. We use a pre-trained VIT B16 as our base model, but we have modified our VIT architecture according to the need. Here also, we used Adam optimizer and binary cross entropy loss function with an activation function as sigmoid. This is the vision transformer architecture. We have multiple layers, and then before each layer, we have a dropout of 0.2. This is the VIT's performance. We have a training, validation, and test accuracy of 88% approximately, which also shows that the model has converged correctly. The loss is around 25%, which is better than the baseline. And here, the main thing is that we have a recall of 0.95, which indicates the model has correctly identified 95% of all the actual positives in the dataset. Here also, we have attached our confusion matrix. To conclude, we compare the CNN and the VIT, and as you can see, the VIT performs approximately 8% better for accuracy because of the positional encoding, as it saves the spatial information while pre-processing. For the future scope, we have efficient ResNet v2 model to performed for the overall optimization, and we can better the VIT as well for the accuracy and F1 score. We are also going to try MCC, Matthews correlation coefficient metric value, which is great for binary classification. Thank you.